Hey everyone, welcome back. I'm Justin Angel. Let's get started. We're here today reviewing the multi-layered perceptron and feedforward networks. Recently, where we left off, we were looking at a single perceptron and its activation function and how to implement it. Now, the question is what happens when you have more than one perceptron? And our deliverable for the day is to have a feed-forward network with ReLU² working as it would in a transformer. This is going to be our first real component that we're going to be using in our production training, pre-training for our large language model. Great. So let's think about perceptrons for a moment. We had a single perceptron. What happens if I have multiple perceptrons? Let's say I have multiple inputs into a perceptron. What we do with that is we sum those up. So previously we looked at WX+B. The formula, if you have multiple input, very similar. It's the sum of the weight of the input multiplied by that particular input and a global bias. Let's say that again. Each input has its own weight. We sum up the input times its weight, and then we add a global bias. That global in the sense of like for the all inputs. So the sum of weight and input plus bias. What does it look like when we implement that? And on the right, I wrote code that is intentionally bad but readable. We have the weighted sum is the weight of that index plus the input in that index. You run that through all of the inputs plus the bias. So if the weights are 0.3 and 0.1 and the input is 1 and 100 and then there's only one bias, then the sum total is 18. You can run that in calculator. It kind of works. Okay, great. So that's kind of confusing but not super clear. Maybe we should look at a demo. And this demo is going to be actually pretty involved. We're going to run through multiple examples and we're going to try and do that here within the demo. So first thing we're doing is we could see we start off with one input and one bias and one weight. We added a ReLU function later on. And then here we're going to just change back and go like, hey, actually, let's not look at a ReLU function yet, but let's look at two inputs. So input 1 and input 2 all leading to the same perceptron. So input 1 is at 1, input 2 is at 0.5. Input 1 has a weight of 1.5, input 2 has a weight of minus 0.8. Why is that relevant? Each input can be upregulated or downregulated, right? Based on what we later on learn. And remember, we're trying to learn the English language, so these weights have a lot of meaning. So we could see the math here, 1.5 times 1 plus minus 0.8 times half plus 0.2, overall 1.3. Okay, so I could change the input. Oh my God, this input is now negative, so it went really positive because its weight is negative. If it goes really positive, it's going to start moving us towards the zero. So the higher this input, the closer to zero the output is going to be overall, because there's an inverse ratio between them. This input though, oh my God, if I keep increasing it, the values go up, and if I decrease it, the values go down. We learn a lot from doing that. And then we have one bias that we add at the end. Oh my goodness, a high bias means a higher overall output. A more negative bias means lower input. So we look at every input. Every input has its own weight. For one perceptron, every input has its own weight per perceptron. And then we sum that up. Okay, what happens if you have two perceptrons and two inputs? Wow, this is going to get real complicated real fast, right? So let's look at this diagram together. We have neuron A on top and neuron B on the bottom. We have input x1 and x2 on the left side. And that as a result of that, the Cartesian multiplication of all of these two inputs, two neurons, will have a total of 4 weights. So the weight between neuron A and input and the first input is going to be AW1, whereas it's going to have a different weight associated with neuron B, BW1. Very cool. Total of 4 weights. Why is that important to highlight? because the more inputs we have and the more neurons we have, the bigger the number of weights and biases that we're going to have to learn. Okay, so we have weights here and we have biases here. And then I threw in ReLU back in because now we can like kind of deal with ReLU. But each of these neurons or perceptrons have their own output. So again, if I change the output for the second input, if I change its weight for the second neuron, it doesn't influence the first neuron at all. Really important to notice that each perceptron has its own relationship to each input in the previous layer. Why did I say input in the previous layer? Because now we have two neurons and we have two outputs for them, but maybe our system should only have one output. How do we combine them? We throw in another neuron at the end. Oh my goodness, it's getting real complicated in here, right? We have our two inputs, our two neurons, but those two neurons now fit into another neuron. We moved from a single layered network to a multi-layered network, which I think is really interesting. So here we could see because neuron B is actually really negative right now, it's blocked by ReLU. It's not adding any value into this perceptron here, into the perceptron that combines both of the hidden layer neurons together. So let's look at that again. We have perceptron A. It has two weights, two inputs associated with them. We have perceptron B, two weights, two inputs connected to them, each of them with their own bias. If I bring these values further up though, then perceptron B starts contributing value into the output neuron. Why is that important? Sometimes we could turn off a neuron, sometimes we could turn it on, right? ReLU helps us not necessarily impact the network too negatively when the values are negative. Okay, so now you must be thinking, Justin, what is an actual use case that would ever need to have a multi-layered perceptron like this? Well, there's the XOR gate. So XOR is a concept from comp cites, like something you really only see when you're learning truth table. A truth table could say if the value of the input is 0 or like you could only have zeros or 1 booleans, 0 0 have 0. If it's 1 1 have 0. But only if one of them is positive and the other one is negative, or one of them is true and the other one is false, truth tables, then we will want to have a true output. There is no way to implement that logic with a single perceptron or even a single layer of perceptrons. You just have to like daisy chain multiple perceptrons together in multiple layers. So here, if I turn on option A, our first neuron is contributing values to the output. That's great. If I turn on output B, then it's again neuron A that's contributing values to the output neuron. But if I turn both of them on, they're both going to contribute values, and there's a strong negative value here in the base and the weight, and the second neuron that's going to cancel out everything and send it back negative. So you can see the interaction of multiple neurons, turning them on and off again to get the results that we want to implement this very simple but very complicated truth table. Okay, so that's as far as we're going to go in this demo. We learned about having more than one input, and each of them has its own weight. We learned about having multiple neurons, each with its own input. So now multiple inputs and multiple neurons. We learned about having multiple layers. So multiple inputs with multiple neurons with multiple layers. We did all of that work all the way up. And we saw one very itty bitty tiny example where that circuit is actually critical because there's no way for a machine learning network to represent this concept of either this or that without having a multi-layered perceptron, right? And there's a lot of times in real life, even in language, we want to implement either, but not both. Great. So we looked at that. That's the demo that we were building up for. So we were talking about doing inputs of sums. We should also mention there's perceptrons that are multi-layer. We kind of saw that a moment ago. And in multi-layer perceptrons, we just daisy chain layers. How many layers? However many we want, however many our architecture makes sense for. But now let's do a little bit of terminology because you're going to hear that a lot, probably from me, but also generally. The first layer of any multi-layer perceptron is called the input layer. The last layer is going to be called the output layer. And any layer in between is going to be called hidden layer. Okay, so that's it. That's just what we wanted to like fully understand here. Why do we call these networks fully connected, or FFNs? If every neuron is connected as an input to every output to every neuron in the next layer, we call it a fully connected network, or an FFN for short. As you can tell, I'm using MLP and FFN as pretty much synonymous. They're pretty much synonymous in the concept of LLMs. Great. So now we showed you a bunch of demos and did a bunch of terminology. Let's look at like a little bit of math and build up intuition. First thing I do, I make a copy. Oh goodness. And then we're going to work in the without answer sheet. Here we have our single input neuron. Neuron is misspelled. Here we go. I'll correct that. So our input is 1, our weight is 1.5, our bias is 2. How do we write that? Okay, we've done this hundreds of times before. Input times weight plus bias. Hundreds of times for me, maybe third or fifth time for you. Okay, now what happens if we have a multi-layered input? We should delete this. This shouldn't be here. Then we can do input times weight plus input times weight plus the bias. 3.1. We could see I took the same values you could see here in the demo on the right, and they're actually explained right here. And like if you want to like see the math, but you could see the output is correct. Okay, great. Now I'm gonna do a little sleight of hand on you. Really fun. I'm going to use something called a matrix multiplication, or a MatMul, or a MMULT. All three of those are names for the same things. I'm going to use MMULT because that's the name of the function in Excel, or sorry, in Google Sheet. I'm going to say multiply this array with this array, and then add 2 to the bias. Why is that not going to work? Because I had the order wrong. The second thing you multiply is always going to be first in the order of MMULT. Just a fun thing to notice. Oh my gosh. Oh goodness. One sec. I'm going to kick this array as the second one. Perfect. And now the output is 3.1. Why is MMULT slightly easier to use? Because I don't have to do my own additions and multiplications. We ended up by just building perceptrons at a place where a linear algebra operation called matrix multiplication, or MatMul, or MMULT, ends up being really useful to us, because that is all MMULT does. It just does these additions and multiplications. Okay, cool. We're going to review linear algebra a bit later again. Don't worry about it. But let's look at a multi-layer perceptron. Okay, so now I'm just going to do math by hand again. Input times weight plus input times weight plus the bias for this first neuron, 0.95. This input times the weight that neuron gives it, plus this input plus the weight that second neuron gives it, plus the bias. Okay, now we did that. So we have weight and bias. So now we have to, and we ran these through ReLU. So now I'm going to go this input times the weight that this one neuron gives it, times this input times the weight that that neuron gives it, the output neuron, and its bias. Did we get to the right answer? Close enough. Actually, no, we didn't. Why did we not get the close enough answer? Because I didn't multiply the right value. So let's just stay in this chart for a moment. So we have this chart that shows us the various values and how to multiply them correctly. Awesome. So let's go back here and try and do that with MMULT, or MatMul. I'm going to use array formula. The only thing that array formula adds to us right now is the ability to have multiple cells influenced by the result of math. So instead of doing one MMULT or MatMul per for each neuron, we could do one MatMul for multiple neurons. So now I'm going to just write that down here. You could see that it's multiplying this array, the input array, and the weight array, and then it adds the bias array to it. Wow, we're saving a lot of operations here. This is like a lot cleaner to work with. Then we have the next output we have to have, like combining both of these outputs from the ReLU. So I could just add a space here, and then all of these inputs multiplied by these weights plus the bias. A bit easier to work with. One thing that you may have noticed that I'm kind of like not showing you here is that like I moved all of our inputs into columns, and then there's like a bunch of like, but they used to be rows. Why did I do that? Because we have to maintain matrix multiplication dimensions. They have to be like roughly like the second dimension of the first multiplied has to be the second dimension, the first dimension of the second multiplied. You don't have to remember that, but in order to maintain that, I had to have a transpose function here. So transpose just takes a column and flips it to a row, or takes a long matrix and flips its rows with its columns and its columns with its rows. I think of it as like just flipping something over. Okay, so now if I use transpose, I can maintain my input as a row and my weights is like the way that they were before. And then I'm still going to just transpose and add the biases. Great. And then I could do that here as well. So if I transpose, oh my goodness, like everything kind of is a bit more readable. Because since we're working on readability, one thing is that I don't like is that my biases are in their own weird little world and they're not really, and then I have to add them out at the end. The WX+B, I just have to do addition. Why can't we just move the biases to be their own column in the weights? Because they're, each one of these represents one neuron. That's another neuron. Why can't we just add them to the weights? Well, the answer is I'm going to have to maintain dimensions for MatMul. So one way of doing that is I could move the biases to be part of this matrix, but, or 2D array, but I'll just add a 1 to the input. The 1 means that like it gets, let's not call it canceled out, but doesn't necessarily influence the results of the MatMul. And when I do that, we can see 1.45 and 0.3, which is similar to when I was working earlier here and adding them manually. So we know it kind of works. That's cool. Now I want to do the same thing with these ReLU outputs and these weights. So I'm just going to add a 1 here as well. And wow, we got to 1.69 again. That's really cool for us, right? Okay, so now what can we build up with that? I'm going to scroll down for a second. I can look at the XOR table. So the XOR table, again, 0, 0, 0, 1, right? We want the output to only be 1 for when it's either but not both. So either 0, 0 is always negative, it's always false. 1, 1 is always 0, right? Or however do we want to think about this in true, false, or not? Right, so these are all of my inputs. I'm going to send all of these inputs to this to this neural network together. These are the weights of the matrices. These are the biases that I've created, and these are the same numbers that we saw earlier. We were looking at the XOR gate here, right? Every one of these first inputs have a weight of 1, and the second set of input have 2 and 6 minus 6. So I'm going to go back here. Okay, so I'm going to just MatMul these together. We're going to have to do the little transpose trick we talked about. All right, why is this MatMul with a parameter of 1? Which one did I add? Let's look at the with answer so you don't have to watch me debug this together. Great. So when I MatMul these together and then I MatMul these 8 parameters and with these 4 weights, good, and then I add the biases, you could see that it's actually arriving at like an intermediary that may or may not be correct. But then I'm going to do that again here in the output. I'm going to MatMul it with the weights of the 2 and the minus 6 and the bias of 0. And then I'm going to multiply that with the outputs of that ReLU. And all of a sudden, I got the correct output for my truth table, right? Only the 2 middle options, the one that are 1, 0, 1 and 1, 0, ended up creating the correct outputs, like the positive true outputs. So now I can move my biases into the weight again. We're just doing this little trick where we're adding the biases not as their own row, but as a column in the weights. Then I added a whole column of 1s because that's how you maintain dimensions. We run through the same math, and we arrive at the same truth table at the end. 0, 1, 1, 0, which means that for these 2 inputs, the value is true, and for these 2 inputs, the value is false. Very cool. So we've now implemented our XOR example with MatMul. We're getting very close to building like a full feed-forward network, a full MLP. So now let's look back and scroll up a bit and look at these MLPs. So one fun attributes all of these maintaining dimensions have is we could actually grow our array, and then we can shrink our array. So let's start by creating a bunch of random values here. I'm going to just copy these over. Oh my God, there's a bunch of fun random values here. But if I multiply it with an array or a matrix that's much bigger than it, I'm going to fill this out. It will actually grow the array. So MatMul with this and this. Can you imagine how many multiplication and additions are happening here? Wow. We just took this array, the input, and we grew it by let's say that this was a hidden set of weights. So now we're like, okay, I've got 4 neurons, right? But like I can grow them out, and then each of them deals with this input. Sorry, this is 16 neurons with 4 inputs each. That's what this represents. So now I went from 4 inputs to 16 neurons. That's really cool. And I have a lot more capacity to think about those 4 inputs because I now have 16 neurons thinking about 4 inputs. Okay, so can I shrink that back down? Yes, I can. I'm going to create a bunch of random values. And this is going to be the second hidden state, which is going to like shrink it down. Here we go. So now we have a random set of values, and I can MatMul these hidden values with this intermediary hidden layer activation. And now we're back to 4x4. So now I took my 16 neurons that I had here, and these were the weights, and this is the activation of those weights. So input times the hidden weights created these activations. I could shrink it back down to 4 neurons. Bam, these are the outputs. Why would I do that? Why would I increase 4x and then shrink by 4x? That's how every MLP for every large language model works. You just learned about growing and shrinking. We could have theories about why that's really, really great to do. And maybe I think I'll cover that a bit in the slide deck. But for now, let's just understand that we increased the size by 4x, we grew it, and then we shrunk it back down. Okay, awesome. So we could do a bunch of other fun shrinking operations. We can do input of 5 times 4, and then you could see that then in order to like change the dimensions, right? 5 by 4 multiplied by MatMul by 4.8, right? It's going to create a 5 by 8. We took the first dimension of the input, the last dimension of the hidden value, and that's going to change the dimensions to that. As long as these 2 dimensions here match. This is just a way for us to see that we need dimensions to match. Okay, cool. So I'll create a couple of values in here. I'll create a couple of values here. And then I'm going to want to MatMul them together. And what you're trying to take from this example is that we have to maintain the size, the dimensions, the way that I just mentioned. So this array by times this array. Bam, right? The first dimension here, move to the activation. The last dimension here, move to the activation. But these 2 dimensions, the 4, have to match up. Great. Let's do that one more time. So all we're doing is we're playing around with dimensions. I'm going to just create a bunch of random values. We're learning intuitively how MatMul works in linear algebra. And then how we got to MatMul is through perceptrons. Okay, so now I have these 2 arrays. So what's going to be the final size of the activation? It's going to be 5 by 16, not 8 by 16. That is a mistake. So I'm going to MatMul this weight by matrix by these hidden activations. And again, because these 2 dimensions of 8 matched between these 2 metrics, we can make this MatMul work. If we were trying to MatMul dimensions that don't fit, I'm just going to try and say, actually go only to row 1989. Now I'm trying to multiply by 8 by 15. We're going to have less data here, right? But let's say I try to multiply with less columns, right? So instead of going all the way to the R column, I'm going to go to the Q column. So now the hidden dimension doesn't match. MatMul can't help me, right? That's not a MatMul operation. These two dimensions, the 8 here and the 8 here, have to match. Great. And then lastly, we're going to want to do one more row here. Actually, I'm going to write this from here and scroll. I'm going to multiply. Again, 16 matches, so I can multiply these. I'm going to take this array that's only 1, and this array that's a 5, and this array that's a 5, and this array that's a 5. Here we go. Scrolling is a bit hard. Here we go. So we got a 5 by 1, and we could do that operation because there's the hidden dimension of 16 between them. Okay, so let's think about what we just saw in this Excel spreadsheet. We started off with this really basic example. We then worked our way to doing math by hand. Then we used MatMul, which explained why we needed that. Then we did math for multi-layered perceptrons, right? We added an extra layer. Again, we kept doing it by hand. Then we ended up with using MMULT for multiple layers. You can see it's a bit weird because like now we're using rows and columns in a weird way. So we introduced transposing for that. Right, so now we have transpose in our statements, which just flips columns and rows to make it more readable. Now we learned the trick of like, let's move the biases into the weights, and then that just means I have to add a 1 into the input columns. Then we learned about, hey, we can grow and shrink, right? And growing and shrinking is something every MLP and every large language model does. So then we learned about why growing and shrinking works, because we can maintain dimension compatibility. So 5 by 8, right? That's going to be the output of these two, as long as these two dimensions match the hidden dimensions. And we did that a bunch of times. And finally, we also saw XOR, which is how to implement something that we wanted to, that we thought that we can only implement in a multi-layered perceptron. Perfect. So we did a bunch of Excel work. Now let's do even a bit more thinking about linear algebra, which I kind of snuck up on you. In linear algebra, if you wanted to represent a one-dimensional array, you'd call it a 1D tensor, and then you would use PyTorch.tensor, and you would give it the one-dimensional array, and you would get back a tensor. Why would we do that? Because tensors can live in the GPU, and CPU and arrays can only live in the CPU. I think that statement is true. 2D tensor. Okay, so we have a 2D array here. Let's say we want to represent it as a tensor in a linear algebra. We would write it this way using PyTorch. It also follows the syntax of another library called NumPy. Just worth knowing in general, if you ever hear the word NumPy, they have similar syntax with PyTorch. Okay, so then we talked about transposing 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. We flipped columns and rows. If you ever wanted to do that, you would use .t. Why would you ever want to do that in processing real inputs? It's a bit harder to answer that question. It's something that we have to do as part of attention, would be the shortest version. Then we learned about matrix multiplication. 1, 2 times 3 plus 4, 1 times 3, 2 plus 4. It kind of looks like having multiple inputs to a neuron. Really, this is just representing one neuron with 2 inputs, right? If you wanted to do that in PyTorch, you would use the et multiplier. And then I want to kind of show you a MatMul example that might confuse you, and we'll talk more about that later, about like how MatMul works. It's, let's say I have this 2 by 2 matrix and this 2 by 2 matrix, and I keep using the word matrix and tensor and array kind of interchangeably. That's just me. And we could see it's 0 times 4, which is 0, plus 1 times 5, which is plus 6, which is 0 plus 6, right, equals 6. So you can kind of see how you do these exercises. And this exercise comes from Professor Tom Ye and his website that kind of teaches how to do MatMul by hand. Okay, so then we learned about upscaling and downsampling, downsampling. So linear algebra allows us to grow and shrink matrices by multiplying these with different dimension matrices. It's part of every modern LLM architecture. Geva 2021 explained that the extra size allows models to experiment with patterns and then scrap the ones that didn't pan out. So as you're thinking about why do I need to have growing and shrinking matrices in the middle of my large language model, well, the answer to that ends up being something like it's going to think about a lot of stuff that you're not going to see, and it's going to need a lot of scratchpad that it could write in and then delete later on. So that's what growing and shrinking does. I think that's part of the answer. I also think part of the answer here is this is where we store a lot of information. These very large matrices of weights is where we store a lot of knowledge. There's a lot of roles that these growing, shrinking MLPs play, but the Geva 2021 explanation really explains why they're useful. They're basically a scratchpad within the activations. Okay, so now we did a lot of math, and oh my God, Justin, you told me I don't need linear algebra, but now you somehow got me to MatMuls. Get me back to code. Okay, awesome. So now we're gonna write and we're not gonna redo all of that in code. You can do that later on. What we're gonna do is we're gonna build a custom PyTorch module that has linear layers. So linear layers is just a way of saying an array or a matrix, right? So that's a 2 by 2, 2 columns, 2 rows. Then it goes to a ReLU. Then it goes to linear of 2 by 1. So that's just 2 columns, 1 row. And so we're going to run through that hidden value, 1 ReLU value, 1 output value, and then we're going to implement the init's going to build up the structure. That's how we build every PyTorch module, and the for is going to run you the input through all of those possibilities. And in order to create this MLP, we'll do equals new MLP. We also want to maybe create the values that we saw from previous examples, right? So let's go here. And I think these are the values that are embedded in this example. I think it's for this example. Yes, for this example. So you could see we have the value of like 1 and 0.8. So I just copied these values, 1 and 0.8, into the setup function. So we can just like see an example of this in code. But it's the same circuit you just saw a moment ago. It's the same visual implemented in code. This is a multi-layered perceptron. And then I'm going to run these tensors of 1 and 0.5. Again, 1 and 0.5. These are the same inputs. And then the output is 1.69. We've seen this 1.69 so many times now. Now it's implemented in a PyTorch custom module. Should we write everything as a PyTorch custom module? Go to the previous section, figure out what you think about that, right? In terms of GPU acceleration, is this the right layer for us? Maybe we need a PyTorch compile to make this faster. Okay, so now we have the exact same construction for MLP, the same architecture, but now we're going to put different values in it. These are the XOR values, 2 and -6. Remember, the -6 is going to just cancel out positive if they're both positive. We're going to run that with the values of 0, 0, 0, 1, 1, 0, and 1, 0, and it prints up the correct truth table. Very cool to see. Very cool to see that all we had to do is change the values, and this MLP with 2 neurons and then 1 neuron ended up being able to support XOR as well with different values. So now we have a bunch of exercises for you, and I would love it if you could do these. One is we're going to want to create a feedforward network or a multilayer perceptron that upsamples the weights and downsamples the weight, upscales the weights, downscales the weight, then runs to a ReLU², right? And then we're going to start with a dimension of 768, upscale ratio of 4. And then you just need to create the linear layers here that have an input dimension of this, the input dimension, and then upscales to 4x. And then downscales back down. And then the forward function is already implemented for you. So you upscale, you ReLU, you square, and then you downsample. How does that, what does that look like when we implement that? You have the answer sheet right here. We create a linear layer of like input and dimension, input and then upscale, and then we flip those. Great. So when we run that, we can also print it out, right? And we can see this is what the printout looks like for a ReLU² upscale, downscale, growing, shrinking MLP. This is roughly what the output looks like. So you could see, oh my God, 768 and 3072, 3072, 768, growing, shrinking. We could also print out how many parameters are in each one of these. So about 2.5 million parameters per matrix. So a total of 5 million parameters that are trainable, weights and biases between these. I will now mention that I've been hoodwinking you a bit. We've been talking about biases this whole time, but really one thing that I'm going to start doing, and did I start doing it here? No, but I did it here in this answer for this code. I said bias false. A lot of MLPs and like many LLMs just don't have biases in them. They just disable that. So now we're down to just weights on neurons. And we can have a conversation about why that is, but that's just the reality of how MLPs often get implemented. So we also have bias false. So now you should probably be able to do this exercise. You've read every single line of code here. More exercise you could do is try and code up an end MLP. Right? There's answers here for you if you want to just copy the values. If you want to implement an OR MLP where OR, right, at least one of them has to be positive. You can implement it here using these code. And again, you have the values here, but you could also think about it. You could also code up an MLP that grows to 5 to 8 to 16 to 1, right? And then you have the answer here as well. And then what's the parameter count of that going to be? And then finally, we have the bonus reference for this is the code that we saw earlier in the linear algebra slide. This is how you create a 1D tensor. This is how you create a 2D tensor. This is how you transpose a tensor with .t. And this is how you matrix multiply MatMul two matrices, right? So now you have all of that here as reference in code as well. Great. So we did so much work. Let's make a couple of decisions. I think this is maybe one of the first times we're going to see this kind of slide. How do we build our GPT-2-style large language model? We're going to make a couple of decisions. So first, we're going to have 2 feed-forward networks per MLP. One is going to upsample, the other one's going to downsample. We're going to have a ReLU² in between them, and we're not going to use biases. Why? Because most LLMs just don't use biases anymore in MLPs. Hyperparameters, these are numbers that we can like run ablation test experiments and then try and like figure out if they're the right number. We're going to use 768 for the input size and 372, which is 4x, 3072, 4x on the output. Why are we using those values? Because that's what GPT-2 did. We are building a GPT-2 style transformer. That's all we're trying to do here today. Great. So let's learn a tiny bit more about feed-forward networks. There's 2 demos that you could play around with. This is from computer vision. There's multiple levels of MatMul here. I'm going to draw the figure 2 on a board, and it's going to do a bunch of matrix multiplication. And at the end, it's going to say that the output is 2. It knows how to recognize that. If you go ahead and then you try and render the number 3, then it's going to say that the output is number 3. And the way that it's doing that is it's going from the input layer to the convolution, right? And you can see how each of these kind of like looks at the previous layer. It also uses something called convolution, which we don't need to have in large language models. It's something that's almost exclusively used in computer vision. And then there's the feed-forward network playground from TensorFlow. TensorFlow is an alternative to PyTorch. So far, we've only been using PyTorch and we'll only keep using it. But worth knowing, Google has their own solution. And then in this playground, we have the ability to change how many neurons are in each layer, how many neurons are in each layer, how many hidden layers we have, right? And then we could try and train them to separate out data sets. So for example, here I wanted to train to be able to discern the blue dots from the orange dots, the inner circle. I'm going to run this over multiple times, and you could see, wow, it was able to do that. How was it able to use this MLP by changing its weight and its biases, and differentiate between the blue points and the orange points? It used something called loss. And through loss, it was able to do backpropagation. You don't need to know what loss and backpropagation is at this point. Loss is going to be our next section, and backpropagation is going to be the section right after that. Important to mention, this is how MLPs get used in real life. We use a loss function and then backpropagation. But worth playing around with this playground. It has a lot of great features that you can learn a lot from without necessarily writing code. Let's talk about linear algebra. I kind of snuck that in on you. You do need to kind of have an intuitive grasp on it, or non-intuitive grasp. You could learn the math. So there's several levels I would recommend here. One is Professor Tom Ye has his MatMul by hand book. While that you could just do that, you could do like a bunch of matrix multiplication in like a little Sudoku like book. I would really recommend this book for that purpose. He also is building an online version that's private and not public yet, but he will have something there. You could also sign up to his AI Academy. You could do a bunch of MatMuls by hand. And finally, there's a book by Mike Cohen that's, to me, really well known from his work on mechanistic interpretability. But here, he just wrote a full linear algebra by code example. So if you learn best by code and you want to learn linear algebra, this is a great book to read through. Great, so we covered everything we needed to on MLPs and feedforward networks. You have a bunch of coding exercises. Next up, we're going to learn about loss function. Why do we need loss functions? Because we're trying to get the neurons to have good weights and biases that are going to contribute to the final outcome we're looking for them. In our case, learning English. Awesome. I hope to see you in the next section on loss functions and the one after that on backpropagation.